9, 2 Taylor polynomials. Let's get it. All right, so this brings up some stuff we did earlier in AB, okay, class? We've got Taylor polynomials that we use for approximations, okay? They are polynomial functions that can be used to approximate elementary functions, and primarily we use it for sine, cosine, e to the x, and the natural log of x. Okay, example one, kind of get us started in what this is all about, okay? Let's find the equation of the tangent line of f of x equals sine x at x equals 0. So remember, this is really just linearization, okay? And if we're in BC, which we are, Euler's method is a form of linearization, but getting a better approximation, okay? But this one's asking me to do the tangent line, which would be y minus y1 equals mx minus x1, right, class? And if I'm doing this at x equals 0, well, sine of 0 would be 0. I'm going to have to find x minus 0. Okay, well, what is m? Well, m is going to be equal to the derivative at 0, right? And the derivative of sine of x would be cosine of x, which we're going to put a 0 in, which would be ichi, right? So we put a little ichi in there, and if I wanted to be more accurate, there we go, y equals x. So what that is that's going to go ahead and give me an approximation. Now they're telling me to use that to approximate sine of 0.02. So then I could say sine of 0.2 is approximately equal to, y equals x. Well, if x is equal to 0.2, y is equal to 0.2. So there we go. There's the approximation. Now, they continue this question, and they ask me if that ends up being a over or a underestimate. Well, if we remember our graph of sine, let's make that blue. Our graph of sine, right, looks like this, right, class? Boom, where that would be pi, and that'd be pi over 2. So 0.2 would be about right there, right? So in my approximation was the line y equals x, which happens to be that tangent line right there. So if you look, it happens about right there. And I don't know about you, but that red is definitely over that blue. And since the red is over that blue, this 0.2 would be an over approximated value. Okay, and obviously I could use Euler's method, right, to get something that was a little bit closer to that. Regardless, the tangent line will always be over that curve. And so it would be an overestimate there, okay? All right, here we go. That gives us kind of an introduction of what we are doing. If you notice, that line only works when we're super duper duper close to the curve. And since we're in BC now, what we are going to do is we are going to find even a better representation, okay? And we're going to create a better approximation. So we're going to create a polynomial. And our polynomial is no longer going to be a line. It might be quadratic. It might be cubic. It might be quartic. It might be quintic, right? But we're going to create a polynomial that does even a better job than just creating these lines or 8 million lines like Mr. Euler used to do, right? Example 2. All right, we are not going to go over this right now because it kind of steals the thunder of our next one. But if you want to go ahead and do that, it's more of an observation or exploratory type of exercise. I think we learn a little bit more if we get right into this bad boy. Oh, dude, a couple cool people right here, right? We've got Brooke Taylor. Brooke Taylor's this young female right here. And she was a mathematician that discovered this crazy little formula for a polynomial. And it does a great job of approximating actual function values. So if we take sine of x, for example, sine of x is a pretty difficult function if you think about it. And what Taylor discovered is we have this polynomial that will give a pretty darn approximation of what sine is. And you know what's amazing is we're actually going to create this polynomial approximation. And it's actually what our calculator uses to graph sine and calculate sine in our calculators. And you're going to say, how could it do that? Well, wait till you see how accurate that bad boy is, okay? And then look at this dude. I think I might do it, right? Get that here going like, look at that flow. Rocking that flow. All right, this dude is Colin McLaurin, Mac Daddy McLaurin, all right? And he kind of discovered that, hey, we can kind of get more specific. We center this guy at c equals 0 and use Taylor's help, I kind of have this as my polynomial approximation, okay? And you're like, what the heck does all that mean, right, class? When we do this stuff with examples, it kind of just flows a little bit better. So let's get with it. All right, couple notes. Okay, I do want to make these notes. Note 1. A first degree Taylor polynomial is a tangent line, right? We just did that. First degree, x to the first, it's a tangent line, okay, of f centered at c. This dude right here is the coefficient of your x minus c to the n term. What does that mean? Just wait. We'll do it. Note 3, this bad boy, Colin Maclaurin, not only got his name on a very specific case of Taylor's work, but he also had super big fly hair. All right, and then we got note 4. Taylor and Maclaurin polynomials, you must use the squiggies because it's an approximation, okay? Don't ever use that equal sign. And we'll go through that as we do some problems together. All right, let's roll. Let's get after it. Let's get it. Okay, go ahead and read that stuff. And who knows, maybe I'll ask a bonus question. Maybe I'll ask a bonus question on our next quiz. All right, here we go. Example 3. Check this out. It's actually really cool how it works out. Gave me a lot of space. Don't even got to go to the blank page. All right. Find the Maclaurin polynomial of degree n equals 5. N equals 5. That means I need a degree n equals 5. That means I'm probably going to have to list out 5 of these guys. All right, we're going to do it for sine of x. We're going to create this polynomial function that does a way better job than a first degree Taylor polynomial, right? And we're going to use it to approximate the value of sine of 0.1. Now, if you notice, sine of 0.1, that's really close to 0. So the first thing I'm going to determine is I'm going to center this at 0. If I'm centering it at 0, it is a Maclaurin polynomial, and I should have known that by reading that right there, right? But it's only called Maclaurin is if our Taylor polynomial is centered at 0, okay? Now, in able to do this stuff, I'm going to have to find some derivatives. Okay, so I think it's nice to do this little column I'm about to show you. Do a little side work. Okay, so we got f of x. What's f of x? F of x is equal to sine x. Okay, and guess what? In able to do this right, I'm going to need those coefficients. I'm going to have that formula that's on the other page, so make sure you look at it, okay? And then with that, I'm going to have to also know what f of 0 is. And f of 0, we already know, is 0. Okay, that's not prime, that's f. All right, next we're going to find the first derivative. Okay, and the first derivative, right, because that incorporates the coefficient of my next guy, right? Look at that next page, and we'll fill it all in together. Don't worry about it. And then I'm going to have to know what f prime of 0 is. What's f prime of 0? It is ichi. It is 1. Okay, now let's do f double prime. Hopefully I don't run out of room here. I might start writing a little smaller. It's negative sine of x. Well, guess what? The second derivative of that is still just 0. F triple prime of x. What? That's negative cosine of x. Negative cosine of x. Well, this third derivative centered at 0 or evaluated at 0 would be negative ichi. Okay, how do I write the fourth derivative? 4 tick marks, that get crazy, right? So we do this. Okay, and we should know that hopefully from our AB days. That actually would be positive sine x. And that fourth derivative evaluated at 0 would be 0. And then we got to go to the fifth derivative. Why? Because it asked me to find the fifth degree. Okay, and that would be, sine is just cosine of x. And the fifth derivative evaluated at 0, centered at 0 is not 0. Ichi! All right, so how do I write out this Maclaurin polynomial centered at 0? Well, here it is. Well, one, I use P. Okay, it means it's a Taylor approximation. In this case, Maclaurin. Why Maclaurin? Because it's centered at 0. Okay, put a little 5 here, because it means we're going to degree 5 of x is equal to. Now, you're saying, why aren't you using the squiggies? Well, I'd be using the squiggies if I did this. F of x is approximately equal to that. Let's see how close they are, okay? And we'll see that at the end. All right, so how do I do this bad boy? Well, the formula on the other page, and I'm not going to bring that up. Can I show you real quick? I hope I don't lose what I did here, okay? Okay, we're going to follow that stuff right there, okay? Look at that. Maclaurin polynomial. We're going to find the Maclaurin, which is really just doing the Taylor, but having it centered at 0. Okay, so I'm going to follow that right there. You guys follow with me. I love it. It stayed with me. Ooh, even keep those circles aligned right there. All right, so that's equal to, it says f of 0. Okay, or f of c, which is 0, okay, plus. Okay, and what does it say next? Look at that page. It says f prime of 0. F prime of 0 is ichi, okay, and then it's x minus 0 because it's centered at 0, okay, to the first power. And believe it or not, it's over 1 factorial. We don't show that because it's silly. Okay, and then what's the next term? The next term would be, what does it say here? Ooh, it's minus. And then it's a 0, though, right? It's a 0. So we're 0 times x minus 0 squared over 2 factorial. Well, you're right. That guy goes to 0. Let's keep rolling, right? Because I need the n equals 5, the 5th degree. So I got to get to the 5th degree. That's first. That's second. Okay, so what's my next one? My next one's the third, right? The 3rd degree. So it'd be start -1, x minus 0. And this one's to the 3rd over 3 factorial, right? That's what that coefficient is. It says -1, right? Look above, right? It's always over. This is actually over 0 factorial. Seems crazy, but it's true. Remember, 0 factorial is 1. So 0 factorial, 1 factorial, 2, 3. What's next, class? Well, it's 4 factorial. But guess what the coefficient is for the 4th derivative? It is 0. X minus 4. Whoops, x minus 0. It's centered at 0 to the 4th, all over 4 factorial. What happens? That guy goes to 0. And then the last one, coefficient, because your derivative is 1. X minus 0 to the 5th power over 5 factorial. If I write this dude a little prettier, boom, 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 we get x minus x to the 3rd over 3 factorial. Looks much prettier, right? Plus x to the 5th over 5 factorial. At home, can you guess what the next term would be? Boom, say it right now. If you said negative x to the 7th over 7 factorial, pat yourself on the back, right? But it only said 5th degree, so I'm going to go to 5th degree. And then they're asking me to approximate it at 0.1. Okay, so how the heck would we do that? Let's get out our sweet little calculators. And I'm going to type in that function we just created, which was x minus x to the 3rd. I'm going to divide that bad boy by 3 factorial, alpha window. Factorial is number 9. It's a convenient little way to get it. Plus x to the 5th, right? Divided by 5 factorial. And once again, alpha window is a nice shortcut for some of those things we use all the time in BC. Boom. And then I'm going to zoom 6 it. We'll use a standard graphing window. Let's check it out. What's it look like? What the what? Oh, okay. Looks kind of sine-ish, huh, class? Does it? I don't know. Let's approximate it. Okay, let's approximate it. You know what I actually want to do is how close is that to sine? Let's go down here and let's put in sine x. Boom, boom. All right, let's compare those bad boys. Oh, okay. Oh, snap. What the what? What the what? That looks like it's gosh darn almost identical right in here. Look at that. Look at that. Look at that hand. Right in there. It looks practically identical. Well, let's check this bad boy. I'm going to second quit this guy, get a nice clear screen. I'm going to go alpha trace. I'm going to y1 this guy. It told me to do it for 0.1, right? That's the Maclaurin polynomial approximation at 0.1. What do we get? 0.998. All right, let's see how close that is to the actual. Let's go sine of 0.1. Boom. Let's see how close we are. What the what? Oh my gosh, that's practically identical. And guess what's crazy? Let's go back up here, right? Because we did that when we were doing this thing, right? I asked you to give me the next term. Let's put the next term, and I just want to see if it gets even better, right? We said it would be minus. Let's go x to the 7th now, right, class? Over 7 alpha window 9ers. Oh, I'm feeling great, right? So let's. I'm going to do the next one. What would the next one be? It'd be plus. It'd be x. Some of you might be saying this is kind of like an alternating series. Good for you. All over divided by alpha window. Oh, snap. Could I maybe go factorial and then maybe insert that next bad boy? I need a 9er there. I just want to see how close it is. I might be flipping out if it's like the same thing. Whew. Oh, snap. It's one of these that's taken forever. Okay. It's a polynomial, so it's going to look. What? That looks very signage. That looks very sine-ish. Okay, okay, end behavior models. That makes sense with the polynomial x to the ninth, right? Start down, end up. How close is this to the red? So guess what? If I list more, I might get sine exactly. And guess what? My calculator can do that. Your calculator actually uses that Maclaurin polynomial infinitely to get all these values for sine. Kind of crazy, right? And we saw how good that approximation was. I don't know about you, but I'm that's kind of cool. That's kind of cool. All right, let's go. Let's go. Let's get it. Cool, huh? Is for sure. Example 4. All right, here we go. Example 4, let's check it out. Find the Taylor polynomial of degree n equals 6. Oh, we got to go to n equals 6. Then use that, dude, to approximate the natural log of 1. All right, do they tell me? Oh, they tell me to center it at 1. And hopefully it makes sense to center it at 1 because what we're trying to approximate is our c being 1.1. Not our c, I'm sorry, our x value being 1.1. Thus, we're going to be using a c of 1. And why is that good with natural log? Because the natural log of ichi is 0. Right? All right, so let's go ahead and do this guy. I've got to list a lot of these guys out. All right, here we go. F of x is equal to the natural log of x. Okay, and I need to know f of 1 because it's centered at 1. That answer would be 0. Right? I need to know f prime. F prime of x is equal to 1 over x, or x to the negative 1. You're going to see why it's helpful to write it like that for this particular problem. Okay, and then f prime of 1 is equal to ichi. Okay, what's f double prime? Oh my gosh, I got to go to 6. Come on. Negative x to the negative 2. That means the second derivative evaluated at 1 would be negative ichi. Whew. Third derivative of x would be equal to positive 2x to the negative 3. What would the third derivative be equal to evaluated at 1? Ni, or 2, or dos. Okay, 3, 4. 4 we put in parentheses. I apologize, I got that big pen. You guys know that. Okay, there we go. That means the fourth derivative evaluated at 1 would be negative 6. I've got the fifth derivative now. What would that be? 24. X to the negative 5. The fifth derivative evaluated at 1 is 24. I'm kind of going fast. Please don't make mistakes. Right? Miss Alessio called me out the other day. Okay. What would that be equal to? That's negative 120x to the negative 6. That means the sixth derivative evaluated because it's centered at 1 would be equal to negative 120. All right, let's go ahead and create this dude. Whoops. Let's write f of x is approximately equal to the sixth degree. This is a Taylor polynomial because it's centered at 1, but the Taylor polynomial is equal to this. All right, first dude starts it off 0, right, plus. Next guy is my 1. This is my to the first, so I need my coefficient. It'd be 1. This time it would be x. It's centered at 1, so it'd be minus 1 to the first over 1 factorial. Remember, that first guy is actually over 0 factorial, but that'd be silly, and you can stop writing that if you want to. My next one is negative ichi, right, negative 1. I got x minus 1 squared over 2 factorial. Let's keep rolling. What's my next guy? It is a 2, so I have plus 2. Oh, and always, I mean, it's about that time where the marker runs out, right? So let's finish this bad boy up here. We will try our best. So we're at plus 2, x minus 1, right? But this time it's the third coefficient, so it's to the 3 over 3 factorial. Let's keep rolling. I'm at a minus 6, x minus 1 to the fourth over 4 factorial, right? What's my next one? I'm at 5. So I'm at plus 24. Plus 24, x minus 1 to the fifth power, all over 5 factorial. And then my last guy, minus 120, x minus 1 to the 6 over 6 factorial. There you go. That's my Taylor polynomial centered at 1. And you know what? I'm not going to go crazy. Oh, it does ask me to approximate it. Actually, it's not too bad to approximate it, right? Because if you plug a 1.1 in, right? If I plug a 1.1 in, you're always going to subtract 1. It's like having a 0.1 in there. All right, so, I actually have it. I have it. Okay, I did it here earlier. So I'm going to save us all the work of putting all that bad stuff in your calculators. And believe it or not, let's do this guy in blue. Okay, and then I'll go ahead and get a new screen, okay? But if I do this at 1.1, right? It's plugging a 1.1 in for all of those x's. And if I put all that into my calculator, I get 0.0953. I'll round to 4 decimal spots. All right, let's do f of 1.1, which would be equal to, so if I actually plug in my calculator the natural log of 1.1, I get 0.095. What's the same thing? What a great approximation, right? And so we start the year with tangent lines, first degree Taylor polynomial, right? I mean, that didn't really help me out unless I was ridiculously close. Cool thing now about the Taylor polynomial, okay, or Maclaurin if it's centered at 0, is that it gives me a gosh darn good approximation. So way back in the day, my dudes with those cool here and stuff, they didn't, it was too difficult with them dealing with natural log sines and stuff like that. So they always used polynomials to approximate those functions, and it made it much easier to deal with. Let's get it. Let's roll. All right, here we go. We got a new screen. Let's keep on riding. All right, so now the AP likes to throw stuff like this on there, okay? Suppose that g is a function which has continuous derivatives and that g of 2 equals 3. So they give me like these coefficient thing, and they ask me to write a Taylor polynomial of degree 3 that's centered at 2. So this one here, you just get it. You just get after it, okay? How do I get after it? Well, we write p. It's a third degree, so we're 3 of x. And what's that going to be equal to, right? It's centered at 2. So we start out with that first guy, which is a tree. And then we start out with my first, right? My first derivative, which would be minus 4. It is centered at 2, so we're x minus 2. X minus 2 to the what? To the first all over 1 factorial. Remember, that's getting tedious. You don't have to keep on doing that. My next guy is the second, right? Is my second derivative. So that's my coefficient. It would be a 7. Now remember, the coefficient of these are really negative 4 over 1 factorial. The coefficient for this guy is really 7 over 2 factorial. That would be the coefficient, and it's centered at x minus 2 squared. Remember that coefficient, it's 7 over 2 factorial, right? Go back to those rules, and that's what it told us over, I think, a couple of pages ago. And the last one, my third degree, would be negative 5 over x minus 2 to the third all over 3 factorial. That's third degree. Coefficient would be 5 over 6, right? Because 3 times 2 times 1 is 6. So there you go. That's it. That's how easy that bad boy is. If they asked me for an approximation, I could do that. But let's keep going, right? Let's try to keep this video under 45. Example 6. All right, here we go. Example 6. Use a third degree approximation for e to the x. Woo! E to the x. Well, shoot, I got to get e to the x first. And then it says, use that approximation to evaluate this limit. Compare it to the actual limit. Is that surprising? All right, well, let's do what they said. They want me to come up with a Taylor approximation near 0. So you should have said Maclaurin. Give Colin his hookups. All right, so let's go. This one's nice. F of x equals e to the x. And some of these you have to have memorized. Memorize sine. Comes up all the time. Memorize cosine. Doing a little bit. Memorize e to the x. Okay? And you guys should notice that, oh, this dude's going to be nice. Right? Because what's f prime of x? F prime of x is e to x. What the what? That means f prime of 0 is still just 1. What's the second derivative? Second derivative is e to the x. What's that, dude? Double prime. Oh my gosh, it just keeps on going. Let's not write it, right? I mean, it's crazy, crazy. All right, well, let's go ahead and write down what this Maclaurin polynomial would look like. 3, they say third degree, so that's got to be 3. So let's list out 3 of these guys. I guess I should find one more third, but let's be honest. Oh no, there are answers. Oh, phew. Got some multiple choice answers going on right there. Don't worry, don't go back and look at it. We do it all when we review. All right? All right, here we go. Ichi, 1 plus Ichi, 1. X minus 0, right? X minus 0 to the first over 1 factorial. Plus Ichi, x minus 0 squared over 2 factorial. Plus 1, x minus 0 to the 3. So look at this one. Let's write this dude prettier, right? How would I write it prettier? 1 plus x squared over 2 factorial plus x cubed over 3 factorial. There it is right there. And they want me to use that guy to evaluate this limit. Okay, all right, let's get it. Let's see what it's talking about. It's saying to do a limit as x. Oh, snap. Shame on you. Direct sub, yo. Direct sub is, I actually know they asked me to sub. I'll direct sub to check it, right? All right, so I'm going to sub I'm going to sub that in for e to the x. So it would be 1 plus x squared over 2 plus x cubed over 6, right? I'll do that factorial work. Minus 1 all over 2x. All right, let's do this work here. Well, 1 minus 1, those guys would go away. And then everything has an x in it, right, class? I might run out of space. Let's go ahead and can I get myself more room? Will that go up pretty, please? Sweetie sweet. All right, so we got the limit as x approaches 0. I'm left with x plus x squared over 2 plus x cubed over 6 all over 2x. Okay. I could factor out an x in the numerator. All right, let's take out that x out of everything, and I'm going to end up with 1 plus x over 2 plus x squared over 6 all over 2. Now let's go ahead and evaluate that limit. If I put a 0 in for all of those x's, I get 1/2. Oh, cool. And they want me to check that with the original. All right, let's go back to the original. Well, how are we supposed to do original limits? Well, the way we're supposed to do original limits is direct sub. If you direct sub, you get 0 over 0 for this problem. What happens if we get 0 over 0? We L-hop it, right? So let's L-hop this bad boy. Its derivative of e to the x minus 1 is e to the x. L-hop. Remember, you got to split limits into the numerator and denominator. Let's L-hop. Right, that bottom one, derivative of 2x is just 2. Now let's see if we can evaluate it, and we sure could. We get half. What the what? That's how good these Taylor-Maclaurin, in this case, approximations are. We're able to do limits using the approximated polynomial. I don't know about you, but that seems kind of crazy. All right, here we go. Now, this shows up on the AP. Man, does it throw us for a loop. They give us a Taylor polynomial centered at 0. Once again, give Mac Daddy his hookup. That'd be a Maclaurin because it's centered at 0. What can you say about the signs of A, B, and C? Justify your response. Okay. Well, A is definitely greater than 0, right? Because it is my asymptote. My y-intercept, right? It's my y-intercept. All right, C, I could probably do C, piece of cake. I mean, that's got to be less than 0 because it's concave down, right? And that's just using your knowledge of parabolas, right? And that's what that is, a parabola. But let's bring this back a little bit, okay? How do I get A? A is equal to f of 0. Well, f of 0 we've got right there. What would C be equal to? C would be equal to the second derivative, and it would be over 2 factorial, but the second derivative, well, the second derivative in this case would have to be negative, and that's how I knew that. It's concave down. Okay, well, then what the heck is B? I think B is the toughest of these, but if you think about how we get B in a Taylor or Maclaurin polynomial, that's how we get that coefficient. And f prime would simply be the slope. So what the heck are the slopes of these guys? Well, this is always increasing, right? If that's always increasing, B would have to be greater than 0. Not too bad, right, class? Not too bad at all. I think we got one more. It gets a little bit tougher here. You're going to have to stay with me. All right, there are 3 guys you have to have memorized. You know what? Right up here, there's some space. We didn't do cosine yet. All right, so we're going to do cosine, but we're going to do cosine a cool, funky way. All right, we're going to write down the sine of x. What the heck is sine of x approximately equal to? Do you have it memorized? Right, it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus da. Now, what's the relationship between sine and cosine, class? What's the derivative of sine? It is cosine. Do you think that I could just find the derivative of sine and it would give me the Maclaurin polynomial for cosine? It does. Cray. Okay, derivative of x is ichi. Derivative of this would be drop that tree, right? And I get that. Holy, I kind of noticed something there. Plus, drop that 5, subtract the 1. That 5 over factorial, that 5 factorial is just a coefficient, right? That guy can just come out. Oh, snap. Plus that. How else could I write this guy prettier? 1 minus x squared over the 3's cancel out. That would be 2 factorial plus the 5's cancel out. X to the 4th over, oh, it's the even dudes. Nuh-uh. 7's cancel out. X to the 6th over 6 factorial. Dot, dot, dot. How about it? Okay? How about it? Pretty cool. Pretty darn cool if you ask me. Now, how can we use those guys that we need to have memorized? You better have memorized. Miss Muscati put it on those little cards you got, right? Everybody put it on those little cards you got. You better know what the heck. Sine X is equal to, as a Maclaurin polynomial, cosine of X is equal to, as a Maclaurin polynomial, and e to the X. And there is one more, but we will get to it a little later. Let's get this video done. All right, this one says, now, 2 ways to do this problem. You could do it the super duper 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 long way, or take a shortcut. How could I take a shortcut for this, dude? Well, all you need to do is have this bad boy memorized, right? Which is X minus, what are they asking me to do here? List out the first 4 non-zero. Okay, so that's 1 non-zero, 2 non-zero. But this, you're saying, Mr. Tanaka, that's for sine. You better believe it's for sine, but check this out. You can either do this the long way, which is list all the derivatives out, do the little coefficient thing, or shortcut. What is the shortcut? Well, guess what? All I got to do to get the Maclaurin polynomial for that bad boy is substitute a 2x in for all of these x's. That is it. Amazing. Makes a really, really difficult problem very doable. And it said, this one didn't say 4th degree, right? This one said 4 non-zero terms. 1, 2, 3, and I need a 4th one. Okay? And that is it, believe it or not. You could simplify if you wanted a little bit, but there you go. Okay? I'm going to erase it because I need some room, but that's all you got to do for that one. Hopefully you have an idea of how to do the next one. But in order to do the next one, you better know what cosine x is approximately equal to. Non-zero. So what do we go? Cosine x, ooh, that starts at EG minus, and remember, these are the evens. Okay, boom, that's the 3rd term, and that is the 1, 2, 3, 4th term. All right, now how the heck do I use that? Take a guess. What do you think x times cosine x would be? Well, it's just x times all of that stuff. I guess I'll show all my work, right, class? Because these are your notes. Okay, and you want to have good, complete notes. All right, so let's just distribute. Oh, shame. Squiggy squiggies. Well, this is squiggies, and then that is equal to x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial. Booyah! Not bad, right? Maybe the next one now, it gets a little bit trickier. And what you have to remember is this, okay? Start with what you know and then work stuff in, right? Let's start with what we know. What do we know? We know what e to the x is equal to. E to the x is 1 plus x, right? This is the coolest one because it so works out so smooth. 1, 2, 3, 4. All right, now how do I work it in? Well, the way I would work this in is I would first say, hey, it really wants, shame on me, squiggy squiggies, e to the x squared. And this is the Taylor polynomial for e to the x. But guess what I got to do? All I got to do is substitute a x squared wherever I see an x, right? That's it. And you can simplify, right? Make it look even prettier. Maybe I will for my final answer. Whoa, tree factorial. But guess what? I added, oh, I got to add in a 4. So what's 4e to the x squared equal to? It's approximately equal to, and I apologize, I'm running out of space, so I'm going to skip the step of showing 4 times that whole quantity, but it'd be 4 times 1. Of course, but I'm almost done. So we got 4, right, plus 4x squared plus, that's going to be 4. I won't simplify that, so you have it, okay? X to the 4th over 2 factorial. You could obviously simplify that, and you should. And then my last one would be plus 4x to the 6 all over 3 factorial. And you could actually simplify this too, because 4 has a 2 in it, and so does a 3 factorial have a 2 in it. Booyah! That is it. I think this video is probably around 30. Is it around 30? It might be. You know what? No way, Jose. I'm going to make you do a little bit for me, please. All you got to do for me to be ready to go in class tomorrow is I need you doing 1 through 5 in this worksheet, okay? And I expect you to do that. I could check it. Aloha.